Good evening. Today we are presenting from palm tree fruit waste to galacturonic acid. So what we have to understand first is that pectin is a chemical molecule which is present in the palm tree fruit peels.
Well, the problem that we are addressing is the huge amount of waste that this fruit cultivation generates.
24 at 3 tons of Chontadurus residues, or the peels, are washed and then filtered to remove residues. Finally, are treated.
Then an acid hydrolysis is performed by adding distilled water and chlorhydric acid to adjust the pH to 2.0. This process is carried out at temperature range of 80 and 90 degrees Celsius for 50 minutes with constant agitation to ensure temperature homogeneity and good mixing. This process is essential for the extraction of the pectin and inactivation of enzymes that can degrade it, as well as the elimination of possible microorganisms present. Then it is filtered and is taken to precipitation, and then we realize a second filtering.
Okay, now we turn into the hard process reaction itself. This reaction is carried out using the natural sign pectinase. We enter the pectin, 50 tons of water, and then also acid and base, which are used according to the needs of the process in that specific moment. We have to keep the temperature at 50 degrees Celsius and the pH at 5. Then the product of this reaction is an aqueous solution of the galacturonic acid, which is our product, acid, base, and residual pectin, which could not undergo the reaction that we needed.
Purification processes are made by centrifugation and ultrafiltration to obtain galacturonic acid, which is our product of interest.
Obtain the kinetic parameters, experimental assays were carried out to determine the adequate dosage of enzyme. And with this, different reactions were carried out with a variable concentration of substrate to obtain graphs of product concentration versus substrate concentration, and estimate before initial velocities to later graph them by model of Michaelis-Menten.
Here we have the Michaelis-Menten plot with experimental data and fitted model, and here are the results for Vmax and Km. But how we obtain these data? MATLAB. So here we enter the data of substrate and rates, and when we run this code, we obtain this graphic, and we realize that with the assays performed at the chosen concentrations, it doesn't give us information to know if the enzyme presents any type of inhibition, even though theoretically it is known that it presents an inhibition by substrates. Therefore, for the adjustment of the kinetic model, we assume that it followed the kinetic of Michaelis-Menten. Here is the equation, and when we run, we obtain the graphic, and here we have the data of Vmax and Km.
So initially for this process, we evaluated 5 types of reactors, which are the one you are seeing on the screen right now. 2 of them are batch or semi-batch, and 3 of them are continuous.
Well, continuous reactors provide a higher yield in the process, given that the residence times they handle are lower if we compare it with a reactor that works in batch. This is better for our process because we are working with an enzymatic reaction that has a high speed. Well, this is the CSTR that we propose, and there are the assumptions that we made. And in the other side, there is a PFR with the assumptions that we made.
For the mathematical model, we use the Dampuller number, that is a relation between the rate of reaction of an species A and the rate of convective transport of A, given by this equation. VA is a quantity that allows us to estimate the conversion degree that a reactor can achieve.
To arrive at the equation that we simulated in MATLAB to compare the reactors, we use the Autor-Vogler's algorithm. First, we obtain the design equation for each reactor by making the assumptions for each reactor, obtaining this equation that we can see, and then we make the reaction law. Here we have the first order irreversible reaction, and then we do the stoichiometry and relate the concentration to the conversion. And finally, we combine all the terms in the design equation to arrive at the ones we will simulate in MATLAB. Here we have the code, the volume, the unique variable that will change, and when we run the code, we obtain the CSTR graphic and the PFR graphic, and The purpose is to indicate what volume of the reactor will need to reach or approach a conversion of 100%, and here is the graphic of both reactors.
Well, in the graphic in the middle, we can see that when comparing the two reactors, the one that reach more conversion is the PFR reactor with a conversion of 85%, and the CSTR reach a conversion of 66%. Well, we noted because the last value of the intercept between the conversion and the Damn-Color number is the specific conversion with a volume of 500 liters. That is the one that we are evaluating.
So in conclusion, after evaluating the two proposals with the same calculation basis, which is the tons of pills that enter the process, we found out that for the same amount of time, the PFR has a greater substrate conversion, which means that the pectin is able to convert into more galacturonic acid, which means this would be the most efficient reactor.